Of course, you're learning R so that you can be better at using it with statistics and improve your own statistical analysis. So let's pause just a moment and talk about graphs and statistics with factors. Given that I'm focusing now on statistics for a moment and not R, this should be a review for most of you. At least most of this should be a review. Factors are categorical variables. So if all we have is a single categorical variable, that means we're looking at a single factor. What statistics can we look at for a single categorical variable? Frequencies and proportions. That's about it. Graphically, we can use a bar graph or a bar plot to look graphically at frequencies, or, as I prefer because it takes out the effective sample size, to look graphically at proportions. What if we have two categorical variables? Now we can look at cross-break or contingency tables. These will help us evaluate the relationship among the two categorical variables. And graphically, we can look for a relationship with a stacked bar plot. And then you can have one categorical variable and one quantitative variable. We can look at side-by-side box plots of the quantitative variable, where the separation of box plots is created by our factor, our categorical variable. We can look at the quantitative variable as a function of the factor or categorical variable to get t-based confidence intervals for the mean difference. If we have more than two groups in our factor, that is, more than two levels, we can use analysis of variance to both descriptively and inferentially analyze the relationship of the categorical and quantitative variable. Now, these are a few of the most simple situations. Obviously, we could have multiple categorical variables. We could have categorical variables that are response variables instead of explanatory variables, which might suggest doing something like logistic regression or using a generalized linear model. R can do all of that. R can do the most advanced statistical analysis that you could come up with because the people who work with R are among the foremost statisticians and are consistently creating functions to handle the latest and greatest in statistical analytic techniques. But let's go ahead with these three simple situations and use R, where we have either a single categorical variable, two categorical variables, or one categorical variable and one quantitative variable. I'm going to continue on using the Mount Juniper data, which I already have loaded in. Remember that I'm using the data in which I have complete cases. Let's go ahead and stick with that. First, let's calculate the descriptive statistics for a single categorical variable. We have already seen the table function, but there's also the prop table function. The prop table function uses a table result as its argument. So here I'm combining them. We could have gone ahead and stored the table in a separate object and then handed that to the prop table function, or we can combine it like I've done here. Here is a graph for a single categorical variable. I'm going to use bar plot, and I'm going to put in the prop table. So I'm going to rerun the function since I haven't even saved it as an object, which we could have done, but I'm showing you that it's not necessary. The y limit here indicates where I want the top of my y-axis to be. What I commonly do is I run without the y limit in there. Let me go ahead and do that. I'm going to comment out the y limit and go ahead and run this. I don't like the fact that the y-axis stops short of the highest bar. So that's why I changed the y limit from 0 to 0.4 in order to be able to capture those highest bars. Now, descriptive statistics for two categorical variables. Again, the table and the prop table. For the table, we simply put in both of our variables, both categorical variables, both of our factors. For the prop table, we again feed it the table command that we used up above, and you could save this in a separate object. Perhaps that would make it more readable, but I'm going to go ahead and do this all in one shot. And then we put in either a 1 or a 2, depending upon whether we want a condition on rows or columns. So let's run this as it is. So you can see here that I've conditioned on grade level, 3rd, 4th, and 5th grade. If I instead wanted to condition on the score level, I could change this to a 1. And now it's conditioned on score level. So if you want a condition on rows, we use a 1. If you want a condition on columns, we use a 2. Of course, there's a right way to do this depending upon your explanatory variable. Note that if I had swapped the order up here of score level and grade level, then it would have swapped whether I wanted rows or columns. I probably here want conditioned on columns. That is, I want to look at score level conditioned on grade level. So let's do it like this. But if I had swapped these up here in the table command, and then again down here under prop table, then I probably would have wanted a 1 for conditioning on the row. Now let's get the graph. Again, I'm putting in prop table, and I'm again conditioning on columns. Let's suppose we wanted inference to see if these proportional differences that we see across grade level, which are hardly any at all here, to see if in fact we can infer any differences to the population. We can use the chi-square test, and for our arguments, we simply need to put in our 2 factors. No surprise, we have a large p-value because we have such similarity and we don't have a very large sample size. You might think 183 seems very large, but it's not like 20,000, in which case the p-value would go down substantially. Here's a graph for 2 groups with a quantitative response variable. So here I'm going to look at score as a function of score level. Now we're getting box plots. Of course, high is going to be higher than low, and they're not even going to overlap because think about how we created score level. It was based upon score, so there's no surprise here. Here are descriptive and inferential statistics for 2 groups with a quantitative response variable. We use the tapply function. When we use tapply, we put our quantitative variable first, then our factor, and then whatever statistic we want to see for these groups. I want to see the 5-number summary, I want to see the mean, and I want to see the standard deviation. So I'm creating 3 tapply's. And while I'm at it, I'm going to go ahead and do a t-test. Note that we do the quantitative variable as a function of, that little tilde there means as a function of, the factor score level. So here are 5-number summaries for the low and high groups. Here are the means, 59.2 and 76.3. Here are the standard deviations. And down here, we get our confidence interval that tells us that the high group is somewhere between 15 and 19 points higher than the low group in the population that these were taken from. Finally, let's do a graph for more than 2 groups with a quantitative response variable. I'll use grade, so now that has 3 levels of the factor. If we want to obtain descriptive and inferential statistics for more than two groups with a quantitative response variable, we can do the descriptive statistics the exact same way we did for two groups using the t-apply. So here I'm going to get the 5-number summary, mean, and standard deviation by grade level. For inferential statistics, instead of the t-test, we do analysis of variance. But notice how I'm doing that. I'm using a function within a function. The innermost function is a linear model. So I'm obtaining a linear model, modeling score as a function of grade. But once I have that linear model, I want to look at the analysis of variance. So I use the ANOVA function. So here we have 5-number summaries for 3rd, 4th, and 5th grade, means, standard deviations, and the ANOVA table. So this is an overview of some of the simple graphs and statistics that we can do when we have 1 or 2 categorical variables and potentially a mixture of a categorical variable with a quantitative variable.